All right, today we are diving deep into the invisible tug of war that powers, well, pretty much everything, from massive industrial factories to the chemistry happening inside our own bodies.
It really all starts with a simple question, doesn't it? You've definitely felt both of these things. But have you ever stopped to think about what's actually going on? One is literally giving off heat, and the other feels like it's sucking the warmth right out of your skin. How is that possible? Well, the answer is all about a secret energy exchange happening inside every single chemical reaction. You see, every reaction is like a little transaction. It's either spending energy or it's making it. And understanding that one simple fact is the key to everything else we're going to talk about. So, let's break down this whole give and take idea. It turns out there are really only two fundamental ways that reactions handle energy. And you'll see they are perfect opposites of each other. First up, we have exothermic reactions. Just think of our campfire. These guys are the givers. They perform a chemical reaction, and as a result, they release a bunch of energy out into the world, usually as heat. That's why you, the surroundings, feel warmer. Heat is basically a product of the reaction. And on the flip side, you've got endothermic reactions, like what's happening in that instant cold pack. These are the takers. For their reaction to even happen, they have to pull energy in from their surroundings. And as they absorb heat from whatever's touching them, they make that environment feel ice cold. For these reactions, energy is a reactant. And this table just lays it all out side by side. For endothermic reactions, you have to constantly put energy in to get to the products. It's like you're pushing a boulder up a hill. But for exothermic reactions, the products are actually at a lower energy state, so the reaction basically rolls downhill all by itself, releasing all that extra energy on the way down. And you know, this really gets to the heart of it. We can see the cool, colorful results of a reaction happening in a beaker, but the real power, that comes from understanding the invisible forces that are actually driving it, because that's how we go from just watching something happen to actually taking control. So let's talk about that control and about balance. See, most reactions don't just run from start to finish and then stop. Nope. Instead, they find a kind of middle ground, a point of balance. We call this dynamic equilibrium, and that word dynamic is so important here. It means things are absolutely still happening. Reactants are turning into products, but at the exact same time, products are turning right back into reactants. That's it, exactly. It is not a standstill at all. It's more like a perfectly balanced, busy, two-way street. Imagine you have the same number of cars going north as you have going south. The traffic is constantly moving, right? But the total number of cars on each side of the road doesn't really change. That's dynamic equilibrium. Okay, so if reactions are this perfectly balanced two-way street, what happens if we mess with the traffic? What if we say close a lane? Well, as it turns out, there's a rule for that. A very, very famous one. This right here is Le Chatelier's principle, and it is the absolute #1 key to controlling chemical reactions. All it says is that if you take a system that's in balance and you push it, it's going to push back. It's basically the fundamental rule of chemical self-correction. Honestly, this is the easiest way to remember it. The reaction has a happy place, a state of balance it wants to be in, and if you do anything to disturb it, it will actively fight back to get back to that balance. It's not passive, it's reactive. So, here's the crucial point. If we know the system is going to fight back, we can actually use that to our advantage. By intentionally messing with the equilibrium in very specific ways, we can force it to do what we want. These disturbances, these are our levers of control. Our first lever is probably the most straightforward one, concentration. What happens if we just add more of a chemical or take some away?
Well, according to Le Chatelier's principle, if you dump in a bunch more reactants on one side, the system says, whoa, too much of this stuff, and it tries to use it up by shifting the reaction to the other side, making more product. And it works the other way, too. If you keep removing the product as it's made, the system will just keep working to replace it, basically pulling the reaction along.
But changing how much stuff is in the pot isn't the only way to tip the scales. Our second lever is temperature, and this connects right back to those exothermic and endothermic reactions we talked about a minute ago.
Here's the trick. Just think of heat as either a product or a reactant. For an exothermic reaction that releases heat, adding more heat is just like adding more product. So the system fights back by shifting away from the products, back towards the reactants. But for an endothermic reaction that needs to absorb heat, adding more heat is like adding a reactant. So the system shifts forward to use it up, making even more products.
And that brings us to our third amazing lever, pressure. This one is especially important when you're dealing with gases. By changing the pressure or the volume of the container, you can totally influence the outcome of the reaction.
And there's a really simple rule for this one. When you increase the pressure, say by squishing everything into a smaller space, the system tries to relieve that pressure. And how does it do that? It shifts to whichever side of the equation has fewer molecules of gas. The side that literally takes up less space. It's that simple.
Now, this isn't just some abstract stuff for a chemistry class. These levers, concentration, temperature, and pressure, are being pulled every single day in massive industrial processes that affect all of our lives. The perfect example is something called the Haber process. To make ammonia for the fertilizer that grows our food, chemists use these exact rules. You see how the reaction has 4 gas molecules on the left, but only 2 on the right? So they crank up the pressure to force the reaction to the side that takes up less space. They also know the reaction is exothermic, so they use a clever compromise temperature that's just right, not too hot, not too cold, to get the best possible yield. It's a beautiful, real-world application of these principles.
So when you really zoom out, you start to see that chemical equilibrium isn't just about chemicals in a flask. It's this beautiful, universal concept. It's a fundamental balance of opposing forces. And this principle, of a system fighting back to find its balance point, applies everywhere in science.
Which, of course, brings us to a final thought. We've just gone through the basic rules that govern how chemical systems respond to change. These same rules are used to create medicines, new materials, and enough food for billions of people. So the question is, now that you know the rules, how would you use them to nudge the world's equilibrium?